The spring mass system that we've been studying in great detail earlier and the simple pendulum have a lot of similarities. But they also have their differences, and I'm going to demonstrate them both in this video. First, let's study the physics of the simple pendulum, which is just a mass suspended by a massless string. First, we'll define the positive movement to be counterclockwise. Counterclockwise, I'm saying because the trajectory of the mass is not linear, but is an arc in this case. And we can see that it is being affected by a restoring force, mg times sine of theta. And because the positive direction is counterclockwise and the restoring force is in the opposite direction, we have a minus sign. Mg sine theta, which is, for small angles, we can approximate the sine of theta with just theta, which gives us mg theta. From a geometry, we can say that theta is the arc length x divided by L. So the restoring force becomes mg times x over L. And let's write it this way, mgl times x. For our spring mass system, we know that the restoring force is minus kx, and we just found out that for a simple pendulum, the restoring force is minus mg over L times x. So the displacement is, or the restoring force is directly proportional to the displacement, but in opposite direction. Exactly the same result that we had for the spring mass system. What about the displacement? For spring mass system, we know that x as a function of time is amplitude times cosine omega t plus phi, the phase angle. In our spring mass system, the restoring force F is always opposite in direction of the displacement. So if the equilibrium position is here, the mass is to the right, the restoring force is to the left. So they're opposite in direction and their directions are parallel. This is exactly the same situation with this. When the pendulum has swung to the right, the restoring force is to the left, and the restoring force is in parallel with its trajectory at any given point. So between these two situations, there's fundamentally nothing different. So because this displacement expression follows from Hooke's law like this, the displacement for the simple pendulum must be exactly the same or similar. So let's still call the displacement x. So it would be x as a function of time is some must be some x max times cosine omega t plus phi. But what is x? Remembering this relationship between the theta, the angle, and the arc length x, we know that x is theta times L. So we can change this to theta as a function of time times L equals theta max times L times cosine omega t plus phi. But because the length of the string is constant, we don't have to carry it around. We can just remove it here. And here we have the expression for the displacement of a pendulum. It is more common to use the central angle as a measure of displacement for a simple pendulum instead of the arc length. For a spring mass system, we know from earlier that the omega here or here is k over m. And for our simple pendulum, we make the same claim, because the only difference in the starting point for our physics is that our force constants are different. In the spring mass system it's k. In our simple pendulum case it's mg over L. So the omega must be of the same form, k over m, where k is now mg over L. So we get mg over L and then the m. The m's cancel. We get g over L. Omega is always also 2 pi times frequency. So frequency is omega over 2 pi, which means that the period, which is 1 over frequency, is 2 pi over omega. And plugging in the value for omega here, we get for the period 2 pi times L over G. So this is the period for a simple pendulum. And it's an interesting result in the sense that it doesn't depend on the mass of the bob. So you can have this string, whatever length, as long as it's same for the both objects, and you can hang a golf ball or a wrecking ball, and the period would be exactly the same in both cases. So the period for the simple pendulum would be 2 pi L over G, whereas for the spring mass system it was found to be 2 pi m over k. So for the spring mass system, there is a mass dependency on its period, but for the simple pendulum, there isn't. Otherwise, they are very similar in behavior, in the sense that they are both examples of simple harmonic motion.